Good morning, everybody, and welcome back to the theory of stellar pulsations. Yesterday, we have started to collect the basic physics and the basic physical principles which govern stellar pulsations, and we have started with considering the mechanics of a flow. So, in other words, we have tried to collect or to derive some of the basic physical equations which describe fluid mechanics. The star behaves like a gas, and therefore its motion is controlled by the equations of fluid mechanics. We have started then with the mass conservation, and we arrived at the equivalent of the mass conservation, which is the continuity equation, either in the Eulerian formulation or in the Lagrangian formulation. The next law of conservation was the law of conservation of momentum. We have considered the change of momentum and applied Newton's law. And in the end, we ended up with either the Euler or the Navier-Stokes equation as the equation of motion. In the next, for the rest of the lecture, we will not deal with Navier-Stokes equation. We will deal with Euler equation. So we drop all the viscosity effects and all the shear stress effects which may occur in a fluid once we consider viscous stress within our configuration. Well, the next equation we want to derive, or which we want to we need an energy equation, and that's what we are about to derive or to consider in the last minutes of last lecture, and to prepare of the change with time of the kinetic energy. It is derived by simply multiplying the equation of motion in the usual way with a velocity vector, and then its particular of 1/2 v squared, which is the kinetic energy. So the first consequence we did within the Lagrangian formulation, we multiplied the acceleration with the velocity vector, which is then the work done by the volume or the external forces plus the work done by the surface forces plus one term left, which we will discuss in a moment. So this is the change of the kinetic energy derived from the equations of motion. This was a preparatory step for considering the energy balance. The energy, the total energy contained in our system, is not only made up by the kinetic energy, it also contains the internal energy. And now the thermodynamics of the and then the thermodynamics of the gas or the fluid, and if you consider a fluid, comes into play. So there is not only kinetic energy, not only mechanical energy, but there is also internal energy, and we write the internal energy as an integral over the volume of the energy density, the kinetic energy density. Is the internal energy per mass, and the total internal energy is then given by this integral over the density times specific internal energy over the volume. Okay, these are the two forms of energies contained in our gas, and we would like to know how this energy there is work done by volume forces. We distinguish between these two sorts of forces, volume forces, for instance, gravity or magnetic fields. These are volume forces, and the work done by the surface forces. These are forces which act on the surface of a mass element. If we consider a mass element, then we can have forces which operate on the surface of this element. So these have to be distinguished from the external or volume forces because they act on surfaces, the other forces act on the volume. Okay, now consider situation on Earth, a terrestrial situation. You have a diesel engine or you have an aircraft engine. There is heat put into the gas because you have combustion in an aircraft engine, or you want to move your truck with a diesel engine. Then you have energy generation, external or chemically generated energy, which puts additional energy into the gas. The situation is similar in a star, but it's not combustion which is happening there, but it's nuclear energy generation, which can provide additional energy and which needs to be considered once we consider the energy balance. So we have to specify an energy generation. For instance, in the astrophysical context, it's the nuclear energy generation, and we design or we denote the specific energy generation. That means the energy generation per mass with epsilon. So this is the specific energy generation, energy per time and mass generated within our gas. Another effect that occurs in any real situation that we have heat fluxes. Heat fluxes means a heat flux is a vector which goes into your mass element through the surface of the mass element. So we have a heat flux which enters, or a part of the heat flux enters the mass element, and some of the heat flux goes out of the element. If the incoming heat flux per surface area is bigger than the outgoing flux, then energy is deposited in our mass element. In the opposite case, energy is taken out of our mass element, and that, of course, in the energy balance has to be accounted for. So we have to consider that there is a heat flux, and this heat flux may deposit or take out energy of our mass element. So if we consider the energy balance, this means the change of kinetic energy plus internal energy, then we need to take into account all these effects. The work done by the volume forces, work done by the surface forces, energy generation possibly, and heat transport might lead to a change or might be needed to account for a correct energy balance. Okay, so let us write down what all these terms. Well, this is the change of the total energy composed of the kinetic energy and the internal energy, change with time in the Lagrangian sense, change of energy in our mass element. Okay, so the first term is the work done by the volume forces. We have convinced ourselves in the previous lecture that this is the term which accounts for the work done by the volume forces. And this here is the work done by the surface forces. It's pressure times velocity times the surface element. So this has to be integrated over the surface. These are surface forces, and therefore they have to be integrated over the surface of our mass element. And then we have The energy generation, which is accounted for by the energy generation rate, specific energy generation rate. If we multiply it with the density, we get the energy per volume and time which is generated, and its integral over the volume will be the energy which is deposited through the energy generation. In astrophysics, it's the nuclear energy generation, and we need to account for the flux, the amount of energy which is deposited or taken out by the heat flux. So we have to integrate the flux over the surface of our mass element, and this will be the flux or the contribution which will either take out or put in energy from the heat flux. And this again is an integral over the surface of the mass element, similar to the surface force, the work done by the surface forces. Okay, now we already saw what we can express here the change of the kinetic energy with time. We derived that term from the equation of motion, and we saw, well, this is the change of kinetic energy. It's given by the work of the surface, the volume forces and the surface forces, and one term left. So we replace in our energy balance, we replace this term by the expression on the right-hand side, and what we see that these terms will cancel with the terms which we already wrote down. Okay, so what is left here? We replace the change of kinetic energy on the left-hand side. We are left with the change of the internal energy, which is the remaining term from the change of kinetic energy. These terms are already present in the change of the kinetic energy, so they will cancel, but there is the one term which is left, which some of you asked already before. This is a volume integral over the pressure times the divergence of velocity integrated over the volume. And then these two terms are left, which need to be taken into account. This is the energy generation, which corresponds to this term, and we have transformed this term from a surface integral into a volume integral. So this is the integral over the surface of the flux is the volume integral of the divergence of the flux over the volume. Okay, now we are left with this equation. And since the volume or the mass element we consider is arbitrary, we can take off the integral and we can say, well, then since the volume is arbitrary, it means that d by dt, rho du by dt, we use the fact that the Lagrangian time derivative of an integral over an integrand, which is written rho times some quantity, is rho times du by dt. This was a consequence of mass conservation, and then we end up with the following equation. Oops. I have some difficulty in where is okay. Okay, so we are left with this equation, rho du by dt. Well, maybe I have to write it down. We made use of the fact that d by dt integral rho u dv is equal to integral rho du by dt dv. This is a consequence of Reynolds transport theorem and the mass conservation which is needed that we can put the Lagrangian time derivative from outside the integral to the second part of the integrand. Okay, so we have rho times du by dt is minus p times the divergence of velocity field plus rho times the energy generation minus the divergence of the flux. So what you see here on the right-hand side, these two terms, this is the energy put into or taken out of the system by energy generation and the divergence of the heat flux. So this is usually, or might be regarded as the heat which is transferred into or taken out of the system. And the rest of it, so this is in terms of thermodynamics, it's the dq, it's usually denoted by dq, the heat change of the heat content of your mass element. And what is the right-hand side? This is the change of the internal energy. And what's that? P times the divergence of V. Fun? It's work then. How do you see that divergence of V has to do with the PdV work in a thermodynamical sense? Well, we have d rho by dt. If you take the Lagrangian form, d rho by dt, we had this before, d rho by dt plus rho times divergence of V, or divergence V is 0. So the divergence of the velocity field in the Lagrangian sense is maybe expressed by d rho by dt, or 1 over rho by dt. Divergence of V is minus 1 over rho times d rho by dt. And rho, if you keep the mass fixed in an element, rho is nothing but 1 over the volume. So d rho by dt is simply dv by dt, or 1 over rho squared, minus 1 over rho squared times dv by dt. So the divergence of V is simply something like the change of the volume, and P times dV is the mechanical work done by the mass element, or the mechanical work which is put into your mass element. So this equation actually represents the first law of thermodynamics. So we end up with the first law of thermodynamics. Well, you may object here, because what have you done? It seems that we have proved first law of thermodynamics. You cannot prove first law of thermodynamics. So actually, our way of arguing with the energy balance was consistent with, so I would like to point this out. What we have done here is we have implicitly done an operation which is consistent with the first law of thermodynamics. We could have gone the opposite way, then we would have ended up with this prescription for writing down or for considering the energy balance. Here we took the opposite way. I tried to convince you about a plausible way to derive the energy balance by collecting all these effects, and it has been done in a way such that we came up with a law which is consistent with first law of thermodynamics. So we didn't prove actually first law of thermodynamics, which is not possible, but we have gone a way which is consistent with first law of thermodynamics, such that after this operation we in a consistent way arrive at the first law of thermodynamics. So that's just as a by remark. This is all consistent with first law of thermodynamics, and we end up with an equation which is suitable for being used in fluid mechanics, which we need for stellar pulsations, but which is, on the other hand, simply the first law of thermodynamics. Okay. So that's just as a remark here. So we end up with first law of thermodynamics, or some version of it at least, which is suitable for treating or for using it in a fluid mechanical environment or for stellar pulsations. Well, there are many forms of the first law of thermodynamics, and one variety of the first law of thermodynamics is to replace this term, the dq, the heat taken out or put into the system, which is, according to first law of thermodynamics, replaced by the change of internal energy and the mechanical work done to the system. Here I've written it in explicit form. This, the divergence of V can be written in a more familiar form through the continuity equation in the Lagrangian form, plus replacing the density by 1 over rho, and then you can immediately derive that this is du by dt, change of the internal energy plus p times dv by dt. So this is actually change of internal energy plus mechanical work, and this is, according to first law of thermodynamics, the heat energy which is transferred to the system. Now heat, the dq, might be in a thermodynamic sense be replaced by the change of the entropy. If we add in some sense the second law of thermodynamics, then the dq, the heat transferred to the system, is simply rewritten as T times the differential of the entropy. So this might be replaced by rho times T by the S by dt. So this is an alternative form, now relying on some further thermodynamic variables. So we replace this, the left-hand side, by rho times ds by dt, and S is the change of the entropy, and S is denoting the specific entropy. So in that sense, if we now replace this left-hand side by rho times T by ds by dt and go back to the upper form of the first law of thermodynamics, rho times ds by rho times T times ds by dt is then given by this term, which changes the heat content of our mass element, which is given by the energy generation and the divergence of the heat flux. Okay, so we have an alternative form of the energy equation. So some people use the upper form, some people use the bottom form, but this is quite nice and short. Rho times T times the time change of the entropy is given by energy generation and the divergence of the heat flux. Well, if the energy generation is not present, and if there is no divergence of the heat flux, then obviously the entropy is constant. That's what we call an adiabatic motion. If the entropy is constant, this is simply the condition, or this is simply another way of saying the motion proceeds adiabatically. It means that there is no heat exchange between the mass element and its surroundings. There is no heat gain or no heat loss in the system. It means dq, or T times ds, is zero. It means the mass element does not exchange heat with its surroundings. What would be the condition for an element not changing its heat content? What is a typical situation? What is needed if you have a flow and elements traveling through your environment? What is the situation when we can assume that this motion is adiabatic? What do you need for that? No heat exchange. The heat exchange must take much longer time then the element needs to travel along the flow. Then the adiabatic approximation is a good approximation. Then if the time needed to for energy to diffuse, for instance, from inside to the outside, if this time is long compared to the time the element needs to travel along the flow, then we can assume it's adiabatic motion. Okay, then the adiabatic approximation would be valid. Okay, so if there is no energy transport, or the divergence of energy is of the heat flux is zero, and if epsilon is equal to zero, then energy does not, entropy doesn't change, and we have an adiabatic motion. Okay, this is a special case of this equation. Now, what is left? Well, we haven't specified, let's go back, we haven't specified our external forces. There is still some unspecified force field or vector field which denotes the external forces, the external volume forces per mass. Well, we haven't specified that. We need to discuss a little bit about these external forces, in particular with respect to our astrophysical situation. Okay, so the forces which might be included in the external forces, well, we will neglect magnetic forces. We don't disregard magnetic and viscous forces, and we consider only forces which have a potential. That means forces which may be written as the gradient of some potential. So this vector field F, which may depend on the position and the time, it may be written as minus the gradient of some potential which depends on position and time. Well, there is one obvious force which we can write in this form and which we need, of course, in astrophysics. This is gravity. And gravity has a potential, and the gravitational potential is given by an integral. The gravitational potential, depending on r and t, is given as minus gravitational constants times the integral over the density at position x and t divided by the modulus of x minus r. This integral has to be taken over x, whereas the potential, it depends on r. So r appears only here. The rest of the variables in the integral depends on position x. Now we take the Laplacian operator acting on the gravitational potential. So the Laplacian operator acts on r. So we can take it underneath the integral because the integral is taken over x. So rho is not affected by the Laplacian. So what is left is rho of x, Laplacian acting on 1 over the modulus of x minus r. Okay, now I have to resort to some functional analysis. The Laplacian operator acting on 1 over x minus r is a delta function. It's minus 4 times the delta function of x minus r. And that means that this is simply this integral over rho, and the delta function will give rho at the position r and t. So I think everybody will be familiar with that analysis. So we end up with an alternative form for determining the gravitational potential, which is Laplacian acting on the potential phi is 4 pi times gravitational constant times the density as a function of position and time. The Poisson's equation for the gravitational potential. Okay, that's for the external forces which we need. There is another thing. Well, Then we have to consider another point which occurs in stars and which is very important in stars. This is the energy transport. So it has to do with the heat flux and how the heat flux changes, or what determines the heat flux once we are in a star. Or you can have also this situation on Earth. You have different temperatures in different places of your environment. Then of course there will be a heat flux from high temperatures to low temperatures, and the same happens in a star. So we have to consider the transport of energy, or the heat flux which goes from higher temperatures to lower temperatures, how this heat flux depends on temperature gradients and so on. So energy transport is the next issue we have to consider, and we will consider energy transport in stars, at least in those environments which are important for pulsations in the so-called diffusion approximation. So we assume that the energy transport is described by a diffusion type equation. That means the flux is proportional to the gradient of some quantity. You can have diffusion of particles, then this would be the flux of particles, which depends, or which is proportional to the gradient of the density of the particles. If you have if the density of particles is not constant, then you will have a diffusion of particles going from high concentration to low concentration, and then we have a flux of particles depending on the gradient of the densities of the particles. And the same can be done with energy transport. Then we have the energy flux. The flux of heat will go from high temperatures to low temperatures. So the origin of the heat flux is a gradient in temperature. Whenever you have a gradient of temperature, you will have a heat flux. Of course, the heat flux goes from high temperature to low temperature, so there has to be a minus in front here. So heat flux is proportional to minus the gradient of the temperature, and anything else which we don't know, we condense into the diffusion coefficient. That's the problem is here, the diffusion coefficient. This is a problem to determine the diffusion coefficient, but we condense all our lack of knowledge into that diffusion coefficient. Okay, this is how we describe energy transport in the interior of a star, and this will be one of the main equations we have to consider once we consider stellar evolution. We will go to stellar evolution shortly, and we will also, this is also important once we consider energy transport in the framework of the treatment of pulsations. Okay, well, if we consider diffusion of photons, we can then make, you have to do a very extensive theory on how it needs some elaborate treatment of how the photons diffuse through your medium. Anything remains the same, but we can specify for the diffusion of photons, we can specify the diffusion coefficient in detail. For diffusion of photons, we have that this diffusion coefficient goes with the temperature to the third. Why does this temperature dependence, how does this temperature dependence come about? Yes, you can. Well, I said, for instance, for the diffusion of particles, the flow of particles, the flux of particles goes with the density of the particles. Well, the flux of energy should be proportional to the energy density. This would be the analog or the parallel argument. So the energy density depends on temperature by the fourth power of the temperature. So the radiation, the energy density of radiation goes with temperature to the fourth, and so you can rewrite this energy density dependence in a temperature gradient. And if you differentiate T to the fourth with respect to the radius, then you get a factor of t to 3 times gradient of the temperature. So that's where the t to the third dependence comes from. Of course, you always have some constants. This is a radiation constant. This is speed of light, an additional factor here. And the essential quantity here, which determines the energy transport, is the so-called opacity. And to determine this opacity is a big business, because you have to take into account all the interaction between photons and matter. You have to consider various processes which go on in an atom, which absorbs photons, which re-emits photons, and all that is condensed in the so-called opacity. And it's a big problem, and it's a big business in astrophysics to determine this opacity. This opacity is the essential quantity in the energy transport equation. We'll come to the details of opacity later on. But this is the diffusion equation and the diffusion coefficient, which is used for the description of energy transport in a star. Okay, so this is another process. Well, diffusion is not the only way how energy is transported in the star. In a star, you may meet the situation. This is also meet in the Earth atmosphere. Sometimes you can see it once the weather is nice. You see that if the atmosphere is heated by the sun, then the blobs of air will rise because they become warm, and this is convection. And by this motion of blobs of material, you can transport energy, and this is called the energy transport by convection. Its origin is an instability of the stratification. So if you have stratification of density and temperature in Earth's atmosphere or in a star, then this stratification may not stay as it is, but it can become unstable, and then blobs of material will rise and some blobs of material will fall, and this motion then will transport simply by its macroscopic motion. It will take energy from the bottom and release it somewhere at the top, and then it falls down again and simply gets energy at the bottom and transports it again to the top. And this macroscopic motion, simply by the macroscopic motion of the matter, will contribute to the transport. And that happens also in a star. Once the stratification becomes unstable, convection sets in, and then we need to calculate how big is the energy, what is the energy transported by this motion. And this is the disappointing thing about it, is there is no theory about it. Well, people nowadays try to simulate convection. The problem is it would need a proper simulation of convection, would need an extremely dense grid. You have to go to very, very small scales, and this is still not possible. So direct numerical simulation of convection is not yet, perhaps it will never be possible to simulate numerically convective motion and convective transport. So what is left here is so-called mixing length theory. I would not like to address it as a theory. It's like an engineering prescription how to calculate the convective energy flux. So it is a summary, or it's several very reasonable physical assumptions which are taken together to provide a prescription how we might describe the energy flux, energy transport by convection. And actually this is one of the basic problems in stellar physics in general, and it's also a big problem for those people who deal with stellar pulsation theory. convection is not, we don't know what to do with convection. It seems to work for hydrostatic stars. The mixing length theory seems to be quite adequate. It leads to reasonable results. There are many uncertainties left, but once it comes to a time-dependent convection, we are lost. So I have to disappoint you at this stage here. There is no theory of convection, and we don't know how to treat convection, in particular in an environment which is time dependent, like stellar pulsations. So the best thing is to go to stars which are not unstable with respect to convection and treat them. Then you are fine. But unfortunately, almost all stars have convection zones, and you are left with this problem. Okay, so just as a cautionary remark, convection is a big problem, and well, unfortunately, I cannot present you any decent theory here. Well, for completeness, I have to mention that we have in degenerate stars, there are some stars where we have heat conduction. It's not only diffusion of photons, but heat conduction, which is, so to say, the diffusion of those particles which have the biggest mean free path in degenerate stars. These are the electrons. So, and this process is called heat conduction in degenerate stars. But this is just for, we will not deal further with heat conduction in degenerate stars, just for completeness of the processes which contribute or might contribute to heat transfer. Okay, so this actually heat transfer or the energy transport is one of the basic of the main parts which also which considerably affects the theory of pulsating stars. Okay, well, there's, for completeness, something is left. We can also change the chemical composition within a star. The chemical composition usually is changed by nuclear processes. There are no other processes which we can have in mind which change the chemical composition. And to calculate the change of chemical composition, we need to invoke nuclear physics, and in a very formal and crude way, I write it down here in the following form, in the Lagrangian sense. So d by dt of, in the Lagrangian sense, of the mass fraction of some species. This could be xi, I denotes the various species. This could be carbon, oxygen, hydrogen, helium. This is controlled by nuclear physics. The change with time of some species is given or depends on the concentration or on the mass fraction of any other elements. So xj denotes those nuclei from which the nucleus I is formed. So it depends on the mass fraction of other species necessary in the process, and on pressure and temperature. It depends also on the thermodynamics of the system. Xi is the mass fraction of element I. And the detailed form of this equation has to be provided by nuclear physics. It's a very complicated form, very complicated dependence on pressure and temperature usually. But I won't go into the details here. Okay, now we are almost done, but we still have two not enough equations for the number of variables. So one equation is still missing, and this equation is provided by the equation of state, by the thermodynamics of the system. That means you have to specify an equation which relates the thermodynamic quantities. That means pressure as a function of density or temperature, or you take the inverse, you write it in the form that density is a function of pressure and temperature. This is the usual thermodynamic basis. So these quantities in the brackets are called the thermodynamic basis. Here the thermodynamic basis is density and temperature, and you express any other quantity in terms of density and temperature, and in this case the thermodynamic basis would be pressure and temperature, and then you write all the quantities in terms of pressure and temperature. For instance, here the entropy can then be expressed as a function of pressure and temperature. Well, this equation of state has to be provided by the thermodynamics. We have to consider what is how our stellar matter might be described, what is important, how these equations of state will look like in detail. We'll come to that later on, and I will give you some examples for the equation of state we use in the stellar environment. Of course, this is the equation which closes the system, and then we have enough equations and enough variables to solve the system mathematically. Of course, some functions still have to be specified, and we will do that later on. This is the opacity. You have to determine the opacity occurring in the energy transport equations. Opacity is also a function of pressure and temperature, and it is a sensitive function of chemical composition. So you need to know the chemical composition, and you need to know the pressure and temperature to determine the opacity. And the same is true for the energy generation rate, the nuclear energy generation rate. It also depends on pressure and temperature, and also on the chemical composition. So these two, this needs to be calculated from atomic physics, and this needs to be provided by nuclear physics. Okay, well, then we are done. If we have all these quantities, well, our task now will be to apply all these equations to stellar structure and dynamics, and we have to solve the resulting mathematical problem. So we have now collected all the basic physics. That was our aim, our goal. Try to solve this system of equations. Well, there is obviously, these equations are too complicated. We cannot assume that we'll have an analytical solution. We have to do it numerically, and there is again some disappointment, because these equations, even if you have a big computer, you can, so far it's not possible. In three dimensions, you cannot solve it. Oops. Okay, we are aiming. Have to disappoint you. It's still not possible to do it in 3 dimensions. It's partially possible to do it in 1 dimension, so in spherical symmetry, and therefore we have to rely to solve the equation, but at the same time, even if we were able to solve all the equations in their complete generality, then the question arises, once we simulate the equation and we get the result, did we understand anything? Of course, all is close to reality or not. We can compare it to the observations, but we have not gained some deeper insight into the problem. A deeper insight into the problem can only gain if we simplify the problem, if we make analytical models for certain aspects, and then we can get some insight. Numerical solution may be fine. A drawback, because we would not, that we cannot solve it numerically. It's not a drawback, because in order to gain some physical insights, we anyway would have to simplify the problem to solve part simplifications and approximations. Okay, that's as a remark. Now let's again summarize the equations which we are going to solve. Well, we have mass conservation, the continuity now in the Eulerian form. We have the momentum conservation. This is Euler's equation here with the Eulerian form containing this non-linear term in the acceleration. This is remarkable in fluid mechanics. This non-linear term causes really much trouble in fluid mechanics, which this acceleration is balanced or is given by pressure gradient, and in astronomy or astrophysics by the gravity. Then we have the energy conservation, or the first law of thermodynamics, either in the form using the internal energy, the change of the internal energy, and the work done, the work done at the mass element, or in the form using the entropy, the change of entropy, which is then governed by energy generation and the divergence of the heat flux. This is the energy equation. Adiabatic motions are characterized by constant entropy. Then we have the energy transport, for instance, by radiation diffusion. Then we can specify the diffusion coefficient. And we have the gravity controlled by Poisson's equation. And nuclear processes, the change of mass fractions is given by nuclear reactions. And we have to specify an equation of state. Here I have included also the dependence on chemical composition, not only the dependence on pressure and temperature. And of course, we need to specify the opacity and the energy generation rate. That's just to summarize what we have to solve and how to proceed now with approximations, with simplifications, to gain some insight into the problem. Okay? Well, first simplification we do not consider a three-dimensional configuration, but we reduce the geometry from a three-dimensional configuration. We reduce the geometry to a spherical symmetric configuration. This is not too bad. If we look at our sun, it seems to be a quite nice sphere. So that might motivate that this simplification is not too bad. We simplify first the geometry, trying to keep all the physics. The physics, try to keep as much of the physics as we can, but simplify the geometry. So going to spherical geometry. Okay, well, then let's stop here and go to the simplification of geometry in the next lecture.